Well, you guys remember back in the first quarter DC electronics, we talked about a circuit here, power supply. It almost looks like a Thevenin equivalent, right? To get maximum power transfer to the load, the input impedance, RG, our Thevenin would have to be, these two would have to be equal. Let's take a look at that in this circuit. How much current can this circuit transfer maximum power? So we need to look at how about the Thevenin equivalent circuit? You remove RL and you take an ohm meter and hook it up where RL was. So you take your ohm meter, hook up from here to here, your virtual ohm meter. How much resistance? This is what we call the output Z impedance of the circuit. How much maximum power transfers are going to be here? So how little resistance here can we actually have in this circuit? One way we can do this is to do the Thevenin equivalent circuit. So rule number one, remove load and measure virtually. So if we remove the load, we're looking into the circuit. Let's see. Let's remove the load. We're looking into the circuit. We see the cap first. We see 4.3 k ohms RE. What else do we see? We have this transistor circuit here. I'll just draw it up like it looks like a transistor. So we see this part of it. On this side, we see R1, R2. We see CN, RG. What do you do with a voltage source? You short a voltage source, and this all goes to circuit ground like this. Now this has a factor of beta with it, and R prime E is on this side of it. So we have 4.3 ohms in parallel with, let's see, 4.3 ohms, k ohms, in parallel with R prime E plus. Now, when we looked at this way, we multiplied everything by beta. So when we look at it this way, we divide everything by beta. This very small current causes a large current flow here, but you see this as a large current. So we have whatever X sub C is in, let's see, R1 in parallel with R2. And according to this, if there's a short right here, then RG parallel with RG over beta DC. So let's figure out what this is going to be. So as we look at this, we've got 4.3 k ohms in parallel with RE, R prime E, which is 25 ohms here. R1 in parallel with R2 is 5K in parallel with RG, came out to 536 ohms. Divide that by the beta DC, which was 100 that we used in the past. We end up with 4.3 k ohms in parallel with 30.36 ohms. And we end up with a 30.144 ohms. So in reality, this RL could be as low as 30.144 ohms to have maximum power transfer.